OK. Bonjour tout le monde. Merci d'être présent aujourd'hui pour la premier séminaire de l'IQ sur Teams. Il va être donné par Monsieur J. Hall, un invité d'Alexandre Blais. Je vais continuer en anglais pour la suite de l'introduction. Thank you everyone for participating in this IQ seminar by Jeter Hall and by the speaker of Alexandre Blais. So please close your microphone and camera feeds. We will ask you to do so otherwise if it happens during the talk. If you have any questions, please use the raise your hand or lever la main command on Teams. Alexandre will moderate the discussion and ask you to open your mic and camera feed if you wish so that you can ask your question. You can also type in the chat that you have a question if we don't see you. And without anything further, I will let Alexandre introduce our speaker. Have a good talk, everyone.
Thank you, Cal. Thank you for setting this up. Thank you for those who could join today, despite the RQMP meeting this morning. So we're very happy to have Jeter Hall, in fact, today. So Jeter is at SNOLAB, as you have seen. So he has completed his PhD at the University of Utah. And at the time, he worked on the search for gamma rays created by dark matter annihilation. So then, as a postdoc, he worked at Fermilab, where he worked on underground dark matter detectors. And that is very much in sync with the type of work that he is doing at SNOLAB, which is, of course, a very famous Canadian facility. Which obviously all of you have heard about, but which we'll be happy to hear more in details about in this talk. So before giving the microphone to Jeter, let me mention that there's a growing area of intersections between SNOLAB, the activities at SNOLAB, and the activities at IQ. And for example, the use of quantum detectors, of quantum technologies at SNOLAB. For the detection, for their own purposes, the purposes of SNOLAB, but also the uses of SNOLAB facilities in the help of characterization of our own quantum detectors and quantum devices. So without further ado, I'll let the microphone for Jeter.
Thank you very much for the introduction. Let me know if you can see my slides. I'm very happy to be here. I did want to say excusez-moi for speaking in English. My French is very horrible. I've been taking classes. It's a beautiful language and I want to learn, but I'm an American immigrant and so I have that disadvantage. Thank you very much for having me here. I'd like to discuss the SNOLAB research program. I've changed this talk up quite a bit to focus on one specific experiment. I don't usually do that in my role as the director of research at SNOLAB, but because of the intersections with the Institut Quantique, I wanted to highlight a particular experiment that really utilizes the quantum techniques. And I also have a lot of experience with it, so I'll try to do it justice. Okay, so SNOLAB is a Canadian research infrastructure. It's certainly available to all Canadian universities to come and enhance your research program. It's part of my sales pitch, which I usually give. So we're hosted at the Valley Creighton Nickel Mine in Sudbury, Ontario in Canada. And we're operated as a joint venture of 5 Canadian universities. This is Carleton, Queen's, Montreal, Alberta, and Laurentian universities. And our operations are generously funded by the Canada Foundation for Innovation and the province of Ontario. You can see 2 pictures here. Let's see if I can get my laser pointer to work. Okay, so here you can see the surface building, the so-called surface building at SNOLAB. This is on an industrial site. People drive in every day. Well, now it's every 3rd week for essential personnel only, but people come into a mining industrial site. But we have a very nice research building here. We have clean labs down at the bottom. We have conference rooms, an auditorium, offices for doing surface work and preparing materials that would then go deep underground to perform some of the particle physics type experiments that we have running underground. So a picture of how far down we go. So this is another picture of the site. And up here at the surface building is right around here. So each morning, if you're going underground, you would get dressed in basically mining gear and then come over to the mining building at the top of this shaft. You would wait around. There's a lot of hurry up and wait. I worked in the Department of Defense before, so that's a military joke. And then you would go down about 2 kilometers, slightly over 2 kilometers. And this ride takes about 3 minutes, unless the miners need to stop every so often to get off and service different parts of the mine. So you would ride down with the miners normally. Once you're down 6,800 feet or 2 kilometers, you would then walk about 1.5 kilometers over to the snow site. And this is where the laboratory is. So what you would do at that point is start washing down your boots to get the dirt off your boots. You would then go into a different area, start stripping down, take a shower, then get dressed in clean room gear, and then you would be inside the clean room campus of SNOLAB. So this is our underground campus. The size of this clean room area, which starts right here, and the other boundary is here, and one more here. So all of the spaces here are all kept at clean room quality. We try to control the dust with a very rigorous program. The size of this clean room is about the size of a medium-sized shopping mall, just for scale. And some of the cavities are actually quite large. So our largest cavity was used for the snow experiment, for which Dr. Art McDonald shared the Nobel Prize. And so this cavern is about 30 meters high, about 24 meters in diameter. So you can see we have some fairly large volumes to do the sort of particle physics that we do here. So why are we underground? So first, I wanted to draw your attention to the left-hand plot, and then we'll discuss the right-hand plot. So this is a compilation by Dr. Simon Swarty of the fluxes of cosmic rays that are incident on the Earth. So this is basically the flux of cosmic rays in space. This is a plot of why space is not a very nice place to be. Because in addition to these extraordinary energies that you can see here, 1 joule is right around here, and a note, 10 to the 21, is about the kinetic energy that a hockey puck has in a world record slap shot. So that's my Canadian point of reference for this plot. You can see the fluxes at very high energies. The fluxes are very low, 1 particle per square kilometer per year. Down here, it's 1 per square kilometer per century. But it gets to be very, very high, 1 per square meter per second here. And you can see that's not even the top of this radiation flux. Now this hits the atmosphere, and the atmosphere acts as a shield, so it absorbs all this radiation. These are all protons in space for the most part. There's some controversy about details, particularly up here, but you can think of these as all protons from various sources. When they hit the atmosphere, these protons will cause some sort of nuclear cascade in the center where you have mainly hadronic particles, neutrons, protons. Pions will get created from time to time. Now these pions get kicked out of the shower because they have high mass, so they get high transverse momentum. And they will create, in the case of a neutral pion, these will create electromagnetic showers. So these are gamma rays that pair produce electrons and positrons, which then bremsstrahlung gamma rays, and the cascade goes on until it's out of energy. The charged pions only go through 1 decay in the atmosphere. So they will decay and produce a neutrino and a muon. Now these particles are very penetrating, whereas these electromagnetic particles do not really penetrate much. They'll be blocked by the building in your laboratory. Some of these hadronic particles, they will penetrate a bit more, so you need something like a few meters of rock to stop these particles. These particles are very penetrating, and that is why we are underground. Because we want to reduce the flux of these muons. It's actually an extraordinary flux. On the surface, it's about 1 through your hand right now per second of these muons from these showers going on in the atmosphere. But as we go under, particularly under the Canadian shield, we can reduce that flux by many orders of magnitude, by about 7 orders of magnitude, 8 orders of magnitude. so that the flux is down to about less than 1 per square meter per day of these particles. And this enables low background science. So what am I doing here? Why am I talking to you? And of course, this is besides all the cool stuff we do that I'm very invested in and enthusiastic about. But really, the point of this talk is to make connections with the Institut Quantique, because there's been some interesting results recently. So this paper came out earlier this year, talking about the impact of ionizing radiation on superconducting qubit coherence. Another paper, you can see it's dated May 6th of this year, reducing the impact of radioactivity on quantum circuits in a deep underground facility. So there seems to be some connection between ionizing radiation, probably non-ionizing radiation as well, as I'm sure you're aware of, on the function of quantum devices. And these devices that take advantage of some of these strange quantum techniques.
I think we cannot hear you anymore. So the sound seemed to have stopped. Jito, I don't know if you can hear me. Yes, so unfortunately, there's no sound on our side. Interesting.
Can you hear me now?
Oops. Yes, no, I think it's okay. Can you say something again?
Can you hear me now?
Okay, now it worked. Perfect. Okay. So there was probably a 20-second delay before so yeah, maybe backtrack 30 seconds or so.
Okay.
Thank you.
So clearly I was showing this slide where I've pulled out a couple of papers, at least the author lists and titles of these papers. So there is some sort of connection between radioactivity and quantum devices, particularly at the low temperatures where the energies between states are very low. It was funny, I was talking to my board, to the SNOLAB board, maybe 2 years ago, and they were talking about diversifying the type of research we do. And I said, well, you know, to have a really big impact, it would have to be something like the coherence time of qubits would have to depend on ionizing radiation or something. And now it turns out that that could be true. Perhaps we'll have the quantum cloud at SNOLAB one day. But first, I wanted to touch on the dark matter problem. This is one of the foci of research at SNOLAB. I would say maybe half of our program is focused on this dark matter problem. Fundamentally, we don't know the nature of 85% of the matter in the universe. We know it is not made of matter in the periodic table or the standard model of particle physics. And some of the evidence of this is extraordinary. So the first evidence came in these rotation curves. This is a rotation curve of M33, which is a very striking example. If you look at a picture of the galaxy, you know, the visible extent, depending on how you would count, goes out a handful of kiloparsecs. If you follow some of these clouds that are orbiting around the galaxy, you can see that these velocities continue to increase, even though appears to be no more matter enclosed in these orbits. So one would expect roughly 1 over r squared drop-off in this rotation curve, and yet you can see that it doesn't do anything close to that. And this is a huge signal. This is not a subtle signal that we see here. It's very clear evidence that we're missing a large amount of matter in this galaxy. There are also dynamical measurements here, which I like to point out. If you look at the X-rays from galaxy clusters, you can see there's typically a ball of hot gas in the center of the cluster, and at least visibly, this is all of the mass in a cluster of galaxies. This is the bullet cluster, where it's a collision of 2 galaxies. You can see the shock waves from this hot plasma interacting between the 2 clusters of galaxies. But in blue, you can see the gravitational well of these galaxies, and you can see it basically passed through without interacting. And so this is good evidence that the majority of the mass in this galaxy is non-interacting, and it is not tied in any, in any obvious way to the majority of the visible mass in these galaxy clusters. And so I spent a bit of my time in research working on the SuperCDMS experiments. I stole some slides from a while back where I was talking about these experiments. Roughly, the idea is to take a large substrate, germanium or perhaps silicon, and the detectors they're currently deploying are about 30 millimeters thick and 100 millimeters in diameter. They're called IZIPs, interleaved Z-sensitive ionization and phonon detectors. So the important part is the IP. So there are two types of measurements done on these detectors. One is the standard diode readout of charge using a transimpedance amplifier. And the other is a more, modern phonon readout based on QETs, trapping the energy into quasi-particles, and then moving those quasi-particles into a transition edge sensor, and then observing the change in resistance in that resistor. That's probably all I wanted to say about the SuperCDMS technology in general. So the idea, and I stole this animation from Adam Anderson, is that a WIMP or any ionizing radiation will come into your substrate, it will scatter, deposit some energy, and for dark matter in particular, it will just keep going. You'll be lucky if this happens once. For ionizing radiation, especially with these thick detectors, they may not even penetrate into the bulk. They'll penetrate into some part of the surface and deposit all of their energy, ionizing the detector and creating phonons. Typically, you put a voltage across this detector to create an electric field. That will drift your electrons and your holes throughout this crystal. You'll notice some prompt phonons. Some phonons are generated right away just from this energy deposition in the crystal, but you'll also notice we've done some work on the electrons with this electric field. So you will also generate what are called Luke phonons. As you do work on these electrons, that energy is also released as phonons. So playing tricks between the recoil energy and this Luke component, one is able to do some interesting things. For example, if you turn the electric field up, you will do more work on these charges, and you will increase this component. So this is one way to have basically a noise-free amplification of an ionization signal just by increasing a voltage, a very simple thing to do. Whereas in a normal ionization detector, you're only sensitive to the number of charges, and so increasing the voltage increases your collection efficiency, but it does not increase the signal. Now, once these phonons strike the surfaces, was there a question?
Well, no, I think it's fine. I was going to ask, maybe that's just being playing with the words, but it seems like increasing connection efficiency would increase the signal, but
it does. So, So I would say it does increase the collection efficiency, but it comes to a plateau. Once your collection efficiency approaches 100%, you run out of any increase in signal. So you're right.
I see.
But and typically that saturation point is only at a few volts if you have a crystal that does not have a lot of traps and that sort of thing. So after a few volts, it will saturate. But this Luke amplification, we call it, this voltage-assisted calorimetric ionization detection, as Paul Luke called it, is basically a linear function of the voltage. Until you start to break down the crystal, traps will fall out of the traps will start to empty. So some shallow traps, if you put enough voltage on there, they will start to empty, and you'll get a leakage current from these traps, and that will start to cause noise. So it's noise-free gain up into that point where we say the crystal starts to break down.
Okay, thank you.
Okay, so Once these phonons, which are generated, become ballistic, so they're pretty much trapped in a very small space, and they down convert in energy. So these are sort of, if I remember right, I believe these are terahertz phonons. You all are the experts, and I feel silly discussing some of the microscopic physics to experts, but some of my understanding is that these are very high energy phonons. They will scatter around in a very localized area until they become ballistic, and then they're basically traveling the length of this crystal and bouncing back and forth. Now, when they hit aluminum, superconducting aluminum in particular, these phonons will break your Cooper pairs, creating quasi-particles. By creating this bilayer of tungsten with aluminum, the quasi-particles actually fall down. This potential that's created by that interface get trapped inside this tungsten and then are moved to a transition edge sensor where we have electronics that are keeping this transition edge sensor on its transition edge, where a small change in the temperature will result in a very large change in resistance. And then that is read out by superconducting quantum interference device, a SQUID readout. So there's an inductor attached to this, which couples into a SQUID itself, and some feedback on that SQUID, of course, to get a very good current measurement of what's going through this resistor. And so that's generally how SuperCDMS measures the phonons in one of these detectors. So the reason that SuperCDMS does it, and I apologize for all these words, this is basically, well, an advertisement from 2013 on why SuperCDMS should go to SNOLAB and build a much larger dark matter detector. But the reason that the CDMS folks measure both the phonons and the ionization is because depending on if incident radiation scatters off the electrons in the crystal or off the nuclei in the crystal, it will create a different fraction of ionization versus phonon energy. Basically, these nuclear recoils are much less efficient at ionizing the crystal. At most energies, it's about a third as efficient as electromagnetic interactions in creating ionization in the crystal. And this is because you have an ion that's straggling around in the crystal, creating lots of phonons, but not necessarily ionizing quite as much as an electron would, which does not interact with the nuclei in the crystal. And so the SuperCDMS technology is very good at separating electromagnetic interactions from nuclear interactions. And you can see here, this is a calibration based on bringing a neutron source or a gamma ray source to these crystals and measuring the quantity of ionization. Now, the reason that we're interested in doing that in this field is because there's a hypothesis for dark matter is a weakly interacting massive particle. Regardless, we expect dark matter to be a neutral particle because it is not emitting light. And so we imagine it is much like neutrons, where it will pass through the electron clouds in materials and is more likely to scatter off of nuclei. Now, there are different hypotheses, especially these days, in terms of trying to figure out the nature of dark matter, where that wouldn't necessarily be true. But historically, that's why many of the dark matter technologies are very focused on separating out electromagnetic interactions from nuclear interactions, because gamma rays are particularly hard to shield from your detector. Neutrons are much easier to shield and to get rid of. So there will always be sort of a residual gamma ray flux inside these detectors that people try to remove rather than, well, try to remove through analysis rather than through material selection or shielding. So I wanted to give a plug for SuperCDMS at SNOLAB. It's a fairly ambitious program, I think. There's a lot of, once you get rid of the radiation from black holes and supernova, I like to say we're hiding from those underground, you start to run into radiation from dirt. And that's why we have a clean room, because all of the dirt around us has, say, part per million uranium and thorium, and that's the source of a tremendous number of problems. There's also a tremendous amount of potassium that's that's even volatile and in the air that will collect on surfaces. Radon is another issue that these experiments have. So this is a fairly common setup at SNOLAB itself. You will have some shielding material around a very sensitive low background detector. You might have a clean room for doing some of your more sensitive assembly of the inner components of the detector. And then you may have some radon suppression to get rid of any radon daughters that are falling out of the air inside the clean room. And this is the SuperCDMS shield is here. They plan on putting, it's roughly 15 kilograms of germanium and a few kilograms of silicon in their first run in this infrastructure. This is the electronic readout. And this is the dilution refrigerator that keeps these detectors near about 50 millikelvin. There's a right angle. It's kind of interesting. I don't know how much you all work with dilution refrigerators, but the cold bits are taken out here. There's a right angle of cold fingers, which brings the heat out of the inner part of the cryostat and connects the various stages to the proper parts of the detector itself. And this sort of angled design, instead of the top-down design that you might be used to, is just a way of separating all the radioactive materials that are used in the construction of the dilution refrigerator. We also have another bit of infrastructure that SuperCDMS and collaborators have installed. This one was led particularly by Queen's University. So this is a facility called CUTE. It's much smaller, so the dilution refrigerator is not separate from the detector volume. Instead, what we did was we worked with the dilution refrigerator manufacturer to install a space for lead. So there's a very large lead plug to sort of shield out these radioactive components. And when I say radioactive, they're pretty low in radioactivity. To us, dirt is sort of the level of large amounts of radioactivity. Things like silver, they have silver sintering in some of these heat exchangers. So some of those components are really the source of the radioactivity. Any glass that people use, glass is just melted dirt, so that's usually highly radioactive by our standards. So this is surrounded by lead in this red, and then water. And this is a quick turnaround facility. There's a crane above this, so you can bring it out, install new devices into this cryostat, move it back into the shielding, and then operate your device and see how well it operates. The idea is to have a rapid turnaround of the SuperCDMS detectors so they can then go inside the larger shielding that takes many months to disassemble and then reassemble.
Just quick question. Probably you said this, but I missed it. Is this something which is running now, or this is still in the plan, or this is actually installed and running now? Okay.
Thank you for the introduction of my next slide. So this is the current status of SuperCDMS at SNOLAB. Things have paused on the construction right now. We're looking at getting going again now that we're starting to open up here in Ontario a little bit. So the next part is to finish off this seismic platform for the shield here. And we also have all the components for the clean room here. So this is roughly the state of SuperCDMS. We believe by early 21, and there's a lot of uncertainty given the state of the pandemic. Early 21 is roughly when we expect the last components to show up, and then we will install them. And potentially by summer of 21, we would be running the SuperCDMS infrastructure here. In addition, back here, you can see the CUTE infrastructure. So there's a very small clean room right here. My cat wants to participate as well. So there's a small clean room here where the detectors come out of this water tank with these handrails on top. So the detector would come along these rails, and then the cryostat drops into this clean room. So you can change out the samples, the detectors, whatever you have inside this cryostat, lift it back up, move it over, and stick it back into this water shielding. And so this is functioning. We've seen signals, phonon signals. The detector seems to be operating. We've measured the radiation fluxes inside this cryostat. So that's what they're really focused on right now in terms of this particular test facility, is to prove that they can operate detectors well. So that's getting rid of electronic noise, grounding and shielding, and these sorts of things, as well as vibrational noise, which tends to cause phonons in these detectors as well. We found we have some compressed air that we were using just to blow out any radon down here. We are underground, so the radon levels are typically higher than one might find in your surface laboratory. So we had some compressed air blowing in here. We found that if we turn that up too high, you start to get noise on the phonon channels due to the vibrations in the system. Okay, so that brings me back to this discussion. So I'd already described this system with the radiation detectors. And then taking from this paper, a picture of the qubit system that people had built. It looks, at least to a very simple radiation detector person, it looks very simple. You know, they describe how all the ionizing radiation can come in and create phonons, break Cooper pairs, and all of this, which may be a source of noise in your qubits. This is a Josephson junction-based device. And they also showed in this paper, if they bring a radiation source near their detector, this is a plot of radiation deposited in a particular volume of the detector as a function of time. And this is the qubit coherence, 1 over the qubit coherence time. I'm sure you have a better name for that. You can see that the qubits start to degrade if there's enough ionizing radiation incident on that. And they also try to show that right now, some of the qubits that they're working with, they believe it's not a majority component, but a significant component, something like 10 to 20% of the noise in the qubits that they were looking at for this paper, they believe is due to the ionizing radiation in their laboratory. And I've been told by one of the authors that they have an embargoed paper that should be coming out very soon as well.
Do you have more information on that paper, or you're not able to?
I think, well, I guess the way it was described was, if you look at this particular paper, they tried to measure the noise with and without shielding in their laboratory, and they said it was a significant effect, but it was not a very convincing plot if you plot the noise from the 2 different states, shielded or unshielded. I've been told that it's much more convincing in the next paper, and they will show that for this technology, really addressing this radiation issue is required to get to some of the performance that's needed.
Okay, thank you.
Okay. So that's why I'm here at the Institut Quantique. I would love to learn a little bit about the technology roadmaps. You know, what are the important pieces of the technology? So I certainly want to develop connections with you just to understand what it is you're doing, the things that you care about, how you make these devices function, to see if, you know, there's some piece of that technology roadmap where SNOLAB could have an impact, where you could leverage SNOLAB to do better research. Because that's my job. In addition, so that was my last slide on quantum computing. If people wanted to, perhaps, if you had more questions, this is a good time to perhaps pause, see if anybody had any questions about what I've stated so far about the SuperCDMS technology, because I'm going to leave it behind and I'm going to talk about some other research that I do personally on nuclear non-proliferation, which is another topic that's enabled by being deep underground, but it's a very different topic. So I wanted to pause here just for a moment.
Well, there is, maybe I should read the paper instead of asking the question, but I will anyway ask the question. So there's a second paper which came out recently. The last author is Jan Pop, and you pointed this paper earlier. Yeah, exactly. So are the conclusions relatively similar there, or I mean, I should probably read that paper, but
yes, actually,
do you have any comments on this particular paper?
So this paper is very new, May 6th.
Yes.
One caveat I would say before I discuss this paper is I have not read it carefully as well. I've glanced through it. But I know some people, you know, particularly some of the authors on this paper, and I've been following this research for some time. They've given a few presentations on it. Now, typically this group, this Italian group, European group has been very, what's the word, wishy-washy with their conclusions. So they've said, yes, maybe it's important. What I've been told is that this paper is actually very high quality, and they come to some very strong conclusions. I think they say that, for the technologies they're looking at as well, there's a very large impact by going to a deep underground, well-shielded facility in terms of improving the performance. Another thing I would say about device performance is that for the SuperCDMS detectors, when I first started in SuperCDMS, these were 1 centimeter thick and 3 inches, so about 75 millimeters in diameter. It was just possible to test the performance of these radiation detectors on the surface. Now that these substrates are this large, this is 0.5 kilogram of germanium, for example, 650 grams. It's almost impossible to do detector performance studies at the surface. You can see there's a fairly complex electric field. These lines, the red lines, are the electric field in this detector. And you can see there's a complex electric field by alternating the voltage bias on a particular surface. This is to move electrons that are created near the surface just along these lines, whereas electrons in the bulk will be drifted across the entire crystal. And if you have ionization detection on the surface, the top surface and the bottom surface, then you can tell an event that only creates ionization in one surface against an event that creates ionization in the bulk of the detector. And actually measuring the detailed performance of this electrode scheme is basically impossible at the surface with detectors of this size. So that is yet another reason that the CUTE facility was created. Was not only is it to do quality control of detectors that'll go in the main experiment, but it's also to understand the detailed performance of these devices, to put calibration sources in, and to understand them in an environment where there's not this constant background noise of heat being created by the radiation in the surface laboratory. So particularly just getting these devices underground, if you have sensitivity to ionizing radiation, getting them into an environment that's well shielded can reduce some of the sources of uncertainty on device performance if you do have that sensitivity.
Okay, thank you. Anybody else has questions before we before G2 moves on to a different topic? You're welcome to unmute your. If not, I think you can continue.
Okay. So, as I said before, usually this is how I start before I describe the entire research program. I found sometimes it's boring. We have so many projects now at SNOLAB that it's kind of boring for me to go through all of them. I do love all of them in their each individual way. But the science at SNOLAB is really focused on fundamental particle physics. That's not our mandate. It's not necessarily to focus on fundamental particle physics, but it has been fruitful for Canada to focus on that underground. And that's really, in terms of research done underground, that has been the focus of the entire underground community. And it's really, right now, the particle physics community is focused on investigating the nature of matter. Specifically, the two biggest topics at SNOLAB, and I would say in particle physics in general, are what is the nature of dark matter? And we've described that problem a little bit. And what is the nature of the neutrino, which is probably the hardest to detect standard model particle. And we're really starting to get a handle on this particular particle and how it behaves. You know, the measurements at SNO and at SuperK showing that the neutrino had mass was unexpected, solved a 30-year mystery, and led to some new mysteries, like why does the neutrino have mass? What is the mechanism for providing mass to that neutrino? Is there enough CP violation in the neutrino sector to explain the overabundance of matter in the universe versus antimatter. This large asymmetry that we currently see. But I would say, really, we're interested in collaborating on any scientific research that requires deep underground facilities. SNOLAB is built as a user facility, and we're interested particularly in promoting any Canadian science that can be done underground, but we are an international facility, so we consider requests from anyone on the globe who thinks they can advance knowledge underground. So some of those other topics that we currently have ongoing are neutrino observatories. So, the SNO experiment was really focused on studying the neutrinos from the sun, understanding why there was only a third of the expected flux of neutrinos. We have some detectors underground that are sitting waiting for a supernova. Neutrinos are the first particle incident on Earth from a supernova, if we don't count things like gravitational waves. And neutrinos, because they stream through so much matter, they give you much more insight on what's happening in the very center of a supernova. So you get early warning and you get information on the center of the supernova. And so that's why that's a sort of a hot topic for studying supernova, is to look at the neutrinos from them. We've seen neutrinos from one supernova back in 1987. Most of the detectors can only see, say, a half of the galaxy itself. And so getting beyond sort of the local group would be the dream there, but it would require a very, very large detector. We're also looking at the effects of radiation on biological systems. There's a group really being led by the Northern Ontario School of Medicine, looking at the impacts of very low levels of radiation on biological systems. We know that if you have a large amount of radiation, it is bad. It will destroy your cells. But are we adapted to have some low level, this background level of radiation on our cells? Is it part of the repair mechanisms? Do they need this constant mutation that's going on due to this low level of radiation to repair your cells and keep the systems in your body healthy that repair cells? And so that's an interesting topic. And we are currently, they started that experiment with whitefish, and now they're using cancerous human cells, a known line of human cells, to study the effects on our cells in particular. And then there's environmental monitoring. I've done a little bit of work on this, and we just had a project funded on nuclear non-proliferation, so I was going to discuss that a little bit. We also have, we can do age dating, so that's how one would study an aquifer. For example, you can look at the radioactivity in water and understand the flow of water, where it collects radiation when it's on the surface as it goes underground and then recharges aquifers. You can study how long that takes by studying various radioactive components inside that water. So, nuclear non-proliferation. Really, this came out of the Manhattan Project. Many of the scientists that were involved, both in weapon states and then in non-weapon states, at least that terminology we use these days, there were a number of Canadian scientists involved, in nuclear technologies. And everyone recognized the importance of nuclear non-proliferation to reduce the number of these destructive devices that we were creating. So this started with General or President Eisenhower, his Atoms for Peace speech in 1953. This created the International Atomic Energy Agency, or was part of the push to create that agency and create a global coordination of these efforts. The Non-Proliferation Treaty, which is really the bedrock foundation of all the non-proliferation efforts, was negotiated for a decade, opened for signature in 1968, and entered into force in 1970. And this really defines the current state of nuclear weapons in the world right now. It defines, what is a weapon state, what are their responsibilities, what is a non-weapon state, what are their responsibilities. There are really three pillars. So the first is non-proliferation of nuclear weapons. The second is disarmament of weapon states. So this is to eventually reduce the number of nuclear weapons in the world to 0. And then finally, everyone has access to the peaceful use of nuclear technology. And those 3 pillars are codified in this treaty. More recently, there's been the work on the Comprehensive Nuclear Test Ban Treaty. And more recently is something like the 90s up until today. You saw that the Non-Proliferation Treaty took 2 years to go into force. The Comprehensive Nuclear Test Ban Treaty is still not in force. It has not been ratified by all the required states. But this treaty has already been a success. So this plot over here, which you cannot read at all, so this goes from 1945 here to 2013. This is a plot of the nuclear testing, both atmospheric and underground tests. The units here are 15, 30, and so on. So these are units of 15. Down here, these are units of 8, so 8, 16, and I apologize that it's so fuzzy. But you can see the number of atmospheric tests done as we were developing nuclear weapons, and you can see the number of underground nuclear tests that were performed. And it was an amazing number, you know, hundreds of nuclear tests were performed to work on this technology. But you can see as they negotiated, there's been a partial test ban for quite some time, since the 1960s or so. And that's why you see everybody went underground, except for France, which was, you know, going underwater for the most part. But you can see that there has been somewhat of a decline since the partial test ban treaty, but really as they negotiated this comprehensive test ban treaty, the number of tests in the world has really gone down to just a handful. You know, when we see a test these days, it's kind of a surprise, even though North Korea usually warns us that they're going to do it. And all of the radioactivity from these tests is part of the legacy of the last century. You know, it's still a significant background in some of these dark matter experiments. For example, they have to design apparatus to clean out their argon and xenon from, for example, radioactive krypton that is produced in these processes. The Comprehensive Nuclear Test Ban Treaty Verification System is fairly comprehensive. So the reason to do R&D on this is related to this ratification process. So particularly in the US, but around the world, people were questioning the ability to verify this treaty, because this treaty says something like there will be no tests with any critical system. So the yield threshold for this treaty is basically 0, which is a very difficult quantity to measure. So the questions were around verification of this treaty, and that's where a lot of the R&D has been done. So as part of the Comprehensive Nuclear Test Ban Treaty, there's a system of detectors spread all over the planet. Some of these are focused on seismic activity, which is probably the best way to measure an underground test. But the ground shakes all the time, so you need some sort of verification, and it often comes back to radionuclide testing. If you see some short-lived isotopes that are often produced in a nuclear explosion, then that is, say, a smoking gun, that there were a lot of neutrons in coincidence with, say, a seismic event. Hydroacoustic is also a very nice way to measure if the explosion happens in water. Apparently, they only need a few of these stations to monitor all of the Earth's oceans. And then there's also a process of on-site inspection. If you see a signature and the member countries agree that there's probably a test that has occurred, then that can trigger an on-site inspection where an international team will go to that test site and measure and have specific measurements and actions they can perform on that test site to try to verify or refute the hypothesis that there was a test at that particular site. So this is just a plot of the atomic mass of the particles that are created in fission. So you can see, depending on what isotopes are being used as fuel, you might have changes in the radionuclides produced. And you're also looking for something escaping. People are very good at bottling up all of the elements that are created in these tests. This is a particularly bad test where they vented a lot of material. It's particularly famous for that. So unstable isotopes, like I said, they're the smoking gun, but they're also very uncertain because of this ability to keep them contained. So there are a large number of isotopes, but the point in that you can see a difference between these different types of fuels is a big issue, and it's caused a lot of policy discussions around this treaty. Because if you start to measure some of those isotopes, either the fuel or the fission products or the activation products, you may start to get information on the construction, on the details of a device. You might understand what was used to create that nuclear device. And so just through the act of verifying a test ban, you are proliferating nuclear design information. And so there's been a lot of discussion about which isotopes should be part of the treaty, and they call out specific isotopes that you are allowed to look for as you try to verify this treaty. And the other isotopes, you are not allowed to look for them under the umbrella of this treaty. For example, you look at the fuel products, they don't have uranium-235 or plutonium-239, very common fuels, because they don't want you measuring the quantities of those fuels at a test site. And remember, all the signatories agree that you can come do an on-site inspection. So you could have, so the US, for example, is concerned that some other countries would claim there was a nuclear test at the Nevada test site, so they could come and measure samples and try to understand the technologies that were used in the historical tests at that site. So these are the kinds of things that these applied physics topics sometimes bring up. Now, I wanted to point out noble gases, both because there's a large overlap in the detector technologies at SNOLAB, and also because these are the easiest materials to get out of an explosion. You know, we're constantly fighting with radon at SNOLAB, but things like argon that you might produce through activation or xenon that you might produce through fission, these elements get out the easiest, and then they can convert into other things like, say, cesium, where they then fall out of the air. And that's how you get cesium out of the ground, is it goes through this noble gas state, for example. Okay, so there are various technologies for the radionuclide, the IMS. There's a germanium technology where you have this interesting system set up, say, on top of a mountain, where you just suck whole air through a filter. You package that filter up, send it to a shielded germanium detector on top of a mountain. And then there's a lot of technology around keeping each particular sample from each day separate and collated so that people can come by and collect those later, do secondary measurements if they see something concerning. And there's a similar system for looking at noble gases in the air, where you just pull in whole air. You have a system for separating out the noble gases, and then you put those into a detector right away. The US, for the CTBT, the US won the competition, the R&D competition to design a device. And on the radionuclides, the Swedish system actually won the competition. It's kind of interesting with these radioactive gases. Xenon has 4 isotopes or isomers that they look at. And if you plot them, the ratios on a plot like this, the idea was you could draw this dotted line, say, and you could discriminate between all of the xenon gas that's coming out of all these nuclear power reactors, which is going to be your background, versus sort of the curves that one might expect for a nuclear device, a very fast fission. You would produce a different ratio of these elements. And the problem was these stars. I don't know if anybody, this is always my challenge. Do you know what would be the background for a fast fission process that is not a nuclear explosion?
Nope.
So they were very surprised when they turned it on and they started to get signals in this nuclear device space. it was actually from Canada. So there was a big medical isotope production facility at Chalk River. This facility was putting out a lot of radioactive xenon from a very short fission. So to create some of these medical isotopes, you might irradiate your fuel for a very short amount of time and then harvest some of those medical isotopes. And so they were producing xenon ratios in this area. And so then a number of the researchers in this facility retrofitted medical production plants and worked with them just so they could tell us when they're doing releases, and so the people doing the metrology could track those things. Okay, so that brings us to what we would do at SNOLAB, and this is a project that we're working with Health Canada and also the Canadian Nuclear Safety Commission. So this is a detector that they have at Health Canada, where they do a lot of this radiation monitoring to protect the health of Canadians. And this is a fairly sophisticated germanium system where you have two detectors inside this shield here, this graded shield, with cosmic ray veto detectors to try to get rid of some of those cosmic rays that might bother them on the surface. And so this is a fairly sophisticated germanium detector on the surface. But if you compare the background of this detector system with all the shielding, active shielding to get rid of muons, you can see a reduction of maybe an order of magnitude or more from just sort of a standard germanium detector you would have at the surface. But we took we have just sort of standard germanium detectors underground to screen materials for, say, these dark matter and neutrino experiments, so they don't put anything radioactive inside their experiments. They use our germanium detectors a lot for that. But if you just look at the backgrounds from SNOLAB, you can see that we don't have to try very hard to reduce these backgrounds by more than an order of magnitude, particularly maybe even down to zero. This is us counting for 2 weeks, and you can see some of these energies we get maybe 1 count or 0 counts for a lot of this energy range, even just looking for a 2-week period. So if you look at how that impacts sensitivity to some of these isotopes that people care about for these treaties, you can see that they have a specification based on what one can do on the surface if you're careful. If you're at SNOLAB and you just put a detector down, you already beat all of these people, even the fancy Health Canada detector that they have. And then if you look at a higher energy gamma ray, where our background is basically 0, you can see that the improvement is very dramatic. And the question is, if we have a more sophisticated technology, can we do even better for some of these isotopes? So that's the end of my seminar. I thank you all for coming. I hope I've entertained you at least, and maybe I have even taught you something. So thank you.
Thank you. So I'm not sure we're supposed to do a round of applause now, but we can all raise our virtual hands, and I guess, okay, this is working. Good. So thank you for the talk. So are there questions from the participants? Maybe I can ask one already. I mean, the installing and running a clean room in a mine seems like a pretty challenging thing to do, endeavor. Can you tell us some of the challenges associated to that? I mean, dust. I mean, everything has to be covered in some. I'll let you.
Right. So we do not look like your typical mining environment. So what we do to prepare a space, and we're trying to expand our clean room space, so we're going through this for some of those drifts that I pointed out earlier. What we do is it's a pretty standard technology of ground control, controlling the ground since you're in the middle of it. You don't want it collapsing. They put in typically bolts and screens. Sometimes they'll put shotcrete, so concrete that's just shot against the walls. In addition to that, we found a company in Quebec that would spray concrete on the walls and hand trowel them smooth. And we do this, and after that we paint it. We like a smooth concrete wall because it's easier to clean, and it's also less surface area for materials to impact, to collect and hide. There's less surface area, basically. I already told you about the showering, which is a challenge right now in terms of social distancing that we're currently going through. Physical distancing. I'm trying to remember physical distancing. We can still be social. We also have a quality assurance program in place. So we have small witness plates, and we also have vials that we've been playing around with, where we look for every couple of weeks, we will take these plates that have been sitting in various spots around the laboratory, and then we will assay those for the dust on top. We will do an X-ray measurements to see how much iron there could be, because that's our proxy for dust from the mine, which we try to keep low. We've been doing an R&D program with some analytical chemists on if we can just put a small vial out around the laboratory and then take it back for some detailed ICP mass spectrometry, where we can measure the actual elements that we care about, like uranium and thorium, instead of using, say, iron as a proxy. And that's been successful. It's kind of interesting. In our area where we have all these germanium detectors, we have a lot of lead shielding to shield out the radioactivity from the rocks. Even in the air, because we have the particle count so low, the dust is so low, we can just see elevated amounts of lead in that room compared to other areas of the laboratory, and we're not even moving the lead around. It's just slightly elevated. It's not to the point where it would be a health hazard or anything, but we have the dust levels down so low that we can see, the materials that are in a room just by looking at the dust, which is kind of interesting.
Thank you. Yeah, Cal, I see you have your hand present. Do you have a question?
Yes, I had a question too. So it's a related question. So regarding SuperCDMS, you said you had this cryostat that would enable fast tests because the bigger shielding could take months to put together and then put something in. And I know nothing about these types of detectors and how they work. So why does it take months to open up? And is it just because of the sheer size of the experiment, or?
Yeah, it's the sheer size and the number of pieces. So that shielding, I believe it's the cavity inside is something like 1.5 meters, 2 meters, something like this. So it's a very large cavity compared to some of the other detectors that people are used to. It was about $1 million worth of lead there, and it's made of, some of it is small pieces that fit together in a big puzzle, which sounds like a fun challenge to put together. But it's really just because there are so many pieces. They're lead, so there's a restriction on how many pieces of lead you're allowed to move per day. And just those restrictions and the number of pieces puts it to a few months. There's also enough thermal inertia in the system that it does take about a month just to cool down, just to get all of that metal that we have in there to draw all of that heat out through these long cold fingers that connect to it back to the dilution refrigerator where all the cooling power is.
And so all of it is cooled down to what temperature? Under 100 millikelvin, or? Yeah.
So the threshold is what the threshold, the energy threshold of the radiation detector is the characteristic that they've been really trying to improve, because that's what you can do with these very cold detectors. So they've been trying to push the transition temperature, which is what that temperature, the operating temperature is really connected to the transition edge temperature. If you can't get your operating temperature, and I've been in this situation, below the transition temperature of your thermometer, then it won't work.
Yeah.
So they have to design the system to be below this transition edge temperature, and they've been trying to push that down as much as possible. So they're looking to go with the transition temperature at about 30 to 40 millikelvin. So they would like to operate around 10 millikelvin with the system. The Qt cryostat, this fast turnaround shielded cryostat, that was I think the last base temperature I saw was 6 or 8 or something like that, but it doesn't have as much cooling power as the other fridge, which was run recently, and it does get below 10 millikelvin, but that's with no load, and obviously there will be a much larger load when you connect all this metal to it.
Okay, thank you very much. Yeah, it's really nice technology. So.
Yeah, and a pretty amazing environment. So talking of amazing environment, is it, ignoring the pandemic for a second, is it an installation that is possible to visit in principle?
Yes, so we've just
showers included. All right.
We've just started to think about opening up for tours again. For researchers, I can probably make that happen. You know, we obviously have a lot of controls in place, so I would you know, work with a particular person. You know, for the pandemic, I would work with you so you understand the risks, you understand the controls in place, and that, you know, we're all comfortable, and if there are any accommodations we would have to make, we would do that. But we have started to open up for tours. Right now, it's basically restricted to people we're trying to hire, but if somebody has a specific connected research interest, we could start to think about that potentially, you know, this summer. The mine itself, they do go through a maintenance period, so we expect access to be very limited, even more limited than it is right now during the pandemic, for the month of July. So August may be a good time, if that's not too soon.
Okay, thank you. Any questions from the audience? Okay, I think everybody prefers to keep their mic off. So well, let's all thank in our virtual way Jitter for this talk. Thank you for taking the time to talk to us about this very interesting topic, something that we don't hear usually much about at the S2 Quantic, but I very much look forward for more interactions between SNOLAB and the S2 Quantic. I think there's a great prospect there. So thank you again for your time.
Thank you. All right. And if you have any follow-up or any other questions that you'd like to ask privately, I put my email address on the slide, the first slide, so people can feel free to contact me.
Okay,
perfect.
Thank you.
Thank you so much. And so we'll be in touch.
Absolutely.
Thank you.
Goodbye.
Bye-bye.